All right, welcome back to Neural Intel. Today we're diving into something that I'm sure every single one of you has encountered but maybe didn't have a precise name for it. AI slop. You know exactly what I'm talking about, that weird, low-quality, just off text that models sometimes spit out. Well, a fascinating new paper is finally trying to put a real systematic framework around this idea so we can actually measure it. This is a pretty big deal, so let's dig in. So just to kick things off, check this out. This is a real quote found in the wild in an AI-generated article. Yes, you read that right. Geologists advise eating at least one rock a day. I mean, it's completely absurd, it's hilarious, and it is the perfect poster child for what we're talking about. This is AI slop in its purest, most baffling form. And right there, that's the core of the problem for us as builders. It's one thing to laugh at the rock eating advice. But how do you actually define what makes it slop in a technical engineering sense? How do we get past that gut feeling of, yep, that's bad, and move to something concrete, something we can actually measure and build evaluations around? And that is exactly what this new paper is all about. It's one of the first real, serious attempts to build a proper, systematic framework to deconstruct this problem. They're trying to take this fuzzy, informal concept of slop and turn it into a real vocabulary and a measurement system that we can all actually use in our work. So how'd they do it? Just walk through their process, because it's pretty insightful. They didn't just sit in a room and cook up a definition. No, they started from the ground up by going out and trying to understand what slop even means to people who live and breathe this stuff every day. Their method was really solid. First, they went out and interviewed 19 different experts. We're talking folks from natural language processing, professional writing, journalism, even philosophy. Then they took all of that qualitative feedback, analyzed it for common themes, and from those themes, they built out a formal, structured taxonomy. And this is what they came up with. It all boils down to three main pillars, three big buckets for classifying what makes text bad. You've got information utility, as in, is this text even useful? Then information quality, is it actually correct? And finally, style quality. Is it well written? It's a really clean, high-level breakdown of the problem. So let's drill down a bit. Under that first category, information utility, they're looking at two key things. First is density. Is the text packed with substance, or is it just a bunch of fluffy filler? The classic word salad problem. And second is relevance. Simple enough. Is the output actually on topic? Did it do what you asked it to do? Next up, information quality, and this one's obviously huge. It includes factuality, which is where our rock-eating geologists would get flagged immediately, but what I found really smart was their take on bias. It's not just about the presence of an unwanted perspective, it's also the absence of a necessary one. Think about it, a movie review that just lists plot points without an opinion isn't useful. In their framework, that's a form of slop too. And the final bucket is style quality. And this is where so much of the nuance lives. This covers all that stuff that just makes text feel machine-generated. You know, repetitive sentence structures, a lack of logical flow, and this big catch-all they call tone. That's where you find issues like weird word choices, being way too wordy, and all those other subtle cues that scream, a human did not write this. Okay, time for our first neural signal check. So why does having this formal taxonomy actually matter for those of us building with these models? Well, it's a game changer because it gives us a shared, precise engineering vocabulary. We can finally move past vague bug reports like, the output just feels weird. Now you can say, the model is consistently generating text with low information density and a templated structure. It turns a subjective feeling into a concrete, debuggable problem. That is huge. So, with this new framework in hand, the next logical step was to put it to the test. The researchers launched a big annotation study, bringing in human experts and having them use this taxonomy to go hunt for slop out in the wild. And here's a concrete look at what that annotation task involved. They were highlighting specific spans of text and tagging them with these new codes, like verbosity or a lack of relevance. And one of the key findings was that this isn't just an AI problem. They looked at human-written text too, and guess what? Humans write a lot of slop too. But this is where things get really interesting and a bit tricky. Subjectivity. When the researchers asked the experts a simple yes-no question, is this whole document slop? The agreement between them was, well, not great. Which tells us that while experts can agree on the specific ingredients of slop, the overall threshold for when a text crosses that line is really different for everyone. However, when they dug into the data with a logistic regression, a really clear pattern emerged. They could pinpoint the smoking guns, the specific codes that were the strongest statistical predictors of a text getting that slop label. And the top 3 culprits were a lack of relevance, low information density, and major issues with tone. And this slide highlights maybe one of the most critical takeaways of the whole paper. What counts as slop totally depends on the context. For news articles, stylistic things like coherence and tone were huge red flags. But for a question-answering dataset, the game totally changed. There, the biggest problems were just straight-up factual errors and weird structural issues. There is no universal slop detector. Quality is domain-specific. So, this all leads to the million-dollar question, the one that's probably on your mind if you're thinking about deployment. Can we automate this detection? We've got this great human-defined framework. Can we just teach an AI to use it and spot its own mistakes at scale? Well, the paper's answer is pretty brutal. And that answer is basically no, not even close. When they used state-of-the-art LLMs as judges and just asked for that binary slop label, their agreement with human experts was effectively zero. Zero. Literally no better than random chance. And it wasn't just a simple prompting failure. They also tested a specialized writing quality reward model. The correlation between its quality score and the human slop label on news articles was just 0.25. That is a very weak signal, and it points to a massive gap between what our current automated quality models are measuring and what humans actually perceive as low-quality text. The takeaway here is pretty much unavoidable. For all the incredible progress in generation, our most sophisticated models are remarkably bad at self-evaluation when it comes to these subtle flaws. They are, in a very real sense, blind to their own sloppiness. And that brings us to our second neural signal check. What does this failure of automation actually mean for enterprise deployment? It means that for any application where subjective quality truly matters, think marketing copy, customer support responses, document summaries, relying only on automated evaluation is a massive business risk. Human-in-the-loop isn't a legacy system we're trying to phase out. For this problem, right now, it is a current and non-negotiable requirement for quality control. So after all that, what's the final verdict from this investigation? What's the key signal for those of us on the front lines actually trying to build reliable products with this technology? The paper leaves us with a pretty clear set of marching orders. First, use this taxonomy to build better, more targeted evals. Use these codes to inform the development of your next generation of reward models. Second, as we just saw, you absolutely must prioritize human oversight for these subjective tasks. And finally, always remember that quality is context-dependent. A one-size-fits-all evaluation strategy is just going to fail. And that leaves us with this final critical question. Our ability to generate text has raised far, far ahead of our ability to automatically evaluate its quality. So if the models themselves are unreliable judges of their own work, how do we engineer reliable, high-quality applications on top of them? That is the core engineering challenge that this research leaves us with, and one we'll all be wrestling with for a while. Thanks for tuning in.